All right, so in this video, we're going to show that every polynomial over a subfield of, every irreducible polynomial over a subfield of C is separable. And we have a helpful lemma first. So suppose we have a non-zero polynomial over a subfield, and let sigma be a splitting field. This is not really relevant. Then F has a multiple 0 in sigma, or in C. We don't need to use sigma here. Your book does. It's not important. If and only if F and df, the formal derivative, have a common factor of positive degree. Okay, so we get a multiple 0 if and only if f and its derivative have a common factor. Now, why in the world should that be? Well, suppose we have a repeated 0. Let's call it alpha. Then I know that f we can write as t minus alpha squared times some g, right? Now, it might be that the 0 is multiplicity 3 or higher, but we know at least since it's repeated, there's at least 2 factors of t minus alpha in there. Okay. All right, then what's the derivative? Well, the Leibniz rule holds for the formal derivative, which is something we're going to prove. So it's the derivative of this product. And the Leibniz rule tells us that it's the derivative of the first guy times the second plus the first times the derivative of the second. And the derivative behaves like usual. So this guy is 2t minus alpha. And you can square that out and check that is true, but it is in fact true. And the derivative of g is, I don't know what the g is, so I can't compute its derivative. It's just derivative of g. But notice there's this common factor of t minus alpha there. Right? And so if it had a repeated 0, then the product rule says that t minus alpha is actually going to show up in the derivative. All right, so f and df have a common factor. Great, so that's the forward direction. Conversely, suppose that f and df have a common factor. T minus alpha in the splitting field adjoint T. Really, it's just in any subfield with access to the roots. Okay. They share a common factor there. That's the, that is, well, sorry, 1 second here. Oh, shoot, sorry, I messed something up. Let me fix that real quick. Dang, sorry. F and df have a common factor in, we don't necessarily have access to the roots, but they have this common factor t minus alpha. Let's let m alpha of t be the minimal polynomial of alpha over k. Then both f and df have alpha as a root because t minus alpha is the common factor. So m alpha divides f and m sub alpha divides df. Thus, f and df have a common factor in k adjoint t. F and df have. All right, sorry, we needed the common factor to be in the smaller field. Sorry, messed that up. Okay, conversely now, suppose f has, okay, so conversely is if it has a common factor, then there's multiple zeros. We're going to do the contrapositive. Suppose f has no repeated roots. And that f and df have a common factor. In k adjoint t, sorry. just messing this up left and right. F and DF have a common factor and the negation, so it's a simple zero. Okay? So we're going for a contradiction, not contrapositive. Okay, then what? Well, F is going to be T minus alpha times G when we pass to the splitting field. Okay. Similarly, df, the derivative, is going to be T minus alpha times H when we pass to the splitting field. Okay. Now, when we differentiate F, we're going to get G plus T minus alpha dg. Right? You just differentiate. That's a linear guy. It differentiates to 1, G plus whatever. Okay, now let's plug in df is T minus alpha H. Okay, so T minus alpha divides 2 of the 3 terms, so it must divide the 3rd term. So G is T minus alpha times some G prime. And then finally, F is T minus alpha times G, but G is T minus alpha times G prime. This has a repeated root. And I don't know why the book wanted to phrase this as a contradiction. We could have just done this directly. But anyways, we have a repeated root, a contradiction. All right. So what is this saying here? That's the end, right? We're saying that the GCD of f and the derivative detects irreducibility. Well, it detects separability if our polynomial was irreducible. So we can detect if we have a repeated root by looking at the GCD of f and df. And then we'll finish the proof of what we started with on the next video. This one took a little bit longer than I thought.